Hello friends, today we are going to look into the basic gates. So what are all the basic gates? Basic gates are AND, OR, NOT, NAND, NOR, XOR, XNOR, bubbled and bubbled OR. Now we'll see one by one what are all these. Now in this particular video we are going to cover the topics like AND gate, OR gate, NOT gate, NAND gate and NOR gate. Now, first of all, what is called basic gates? Basic gates are used to perform logical operations. Boolean functions can be expressed in terms of logical gates. Now, the most important logic gates are AND, OR and NOT. We'll see how all these functions. Now, number one, NAND gate. NAND gate performs multiplication operation. Now, for an example, we take a NAND gate with two inputs. Now, this two input AND gate will give a single output. The same way, an AND gate can also be with three inputs. Three input AND gate also gives single output. Now, for an example, we'll see the two input AND gate. Now, this is the symbol that is represented for AND gate. So, there are two inputs A and B. When these two inputs are fed into this NAND gate, AND gate, we get an output which is equal to multiplication operation A into B. Now this is the expression of a AND gate. Say, let us represent the output as Z. Z is equal to A multiplied by B. Now, our first input is A, the second input is B. Multiplying these two, we get an output that is Z. Now, for two inputs, we can have a combination of 2 power 2, that is 4 different combinations of input can be given to this particular AND gate, and we receive 4 different outputs. So first, if A is supplied with 0 and B is supplied with 0, we get an output 0. That is A multiplied by B will give 0. 0 multiplied by 0 is 0. The same way, supply 0 to A, 1 to B, we get an output 0. Supply 1 to A, 0 to B, we get an output 0. Now, if we supply 1 and 1 for both inputs A and B, we get an output 1. Now this is how we draw a timing diagram for AND gate. So, for instance, first input X, we supply a lower signal, that is 0 input. For another input Y, we supply a low signal, that is 0. So 0 into 0, 0 multiplied by 0, we again get 0, that is the low signal. In the second time instance T2, we supply 0 for X, 1 for Y, that is high input terminal. So X into Y, that is 0 into 1, again we get a low terminal. Now the same way we proceed with all other inputs. Now look here, supplying 1 for X and 1 for Y, we get an output 1, that is high signal. Now this is what we get inference. When at least one input is low, the output is low. When both inputs that is fed into the AND gate are high, we get an high output. Now we'll move on to the next gate, OR gate. OR gate performs AND addition operation. Now here again, OR gate can be supplied with 2 or 3 different input signals. For both, we get only one single output. Now this is a symbol that is represented for OR gate. Now two signals A and B are supplied to OR gate and it gives a single output, that is the operation A plus B. Now, the expression for OR gate is Z is equal to A plus B. Now, again, with two different input signals, we get four combination of inputs. That is 0, 0, we get 0, 0 and 1, 1, 1 and 0, 1, 1 and 1, we get 1. Now, what can be inferred from this particular truth table is, for any OR gate, when at least one input is high, we get a high output. And when both the inputs are low, we get a low output. Now, this is the timing diagram that can be drawn for an OR gate. Now, low signal, we get an output as again low signal. High signal, again high signal. Low and high constitutes again high. So, this is how we can proceed with drawing a timing diagram for OR gate. Now, next we move on to the next gate, that is the NOT gate. NOT gate is usually referred to as inverter gate or complement gate. So, this NOT gate takes a single input and gives a single output. This is the representation of NOT gate. Single input is given and single output is given. A is supplied inside this NOT gate, and A dash or A bar, that is complement of A, is received as the output. This is the Boolean expression for NOT gate. That is A is equal to A dash. Now, we'll move on to the next gate, the NAND gate. NAND gate is the complementary gate for the AND gate. A NAND gate is a combination of NOT gate and AND gate. Now, NAND gate has an output that is normally at logic level 1 and only goes to logic level 0 when we supply low inputs. When all inputs are at logic level 1, the NAND gate becomes inverter gate of NAND gate. Now, this is the digital representation of NAND gate. We supply two inputs to a NAND gate, that is AND followed by inverter gate. We get the output Q is equal to A into B whole dash. The representation can also be made like this. A and B is fed as input to AND gate. We receive an output. This output A into B is fed to a NOT gate, and again we get an output, that is A into B the whole dash, which constitutes the NAND gate. This is the timing diagram for the NAND gate, where when A and B are low, we get a high output signal. When A is high and B is low, again we get only a low output. Now, we move on to the next gate, the NOR gate. NOR gate is a combination of OR gate and NOT gate. The inclusive NOT gate has an output that is normally at logic level 1 and only goes low to logic level 0 when any of its inputs are at logic level 1. NOR gate is a reverse or complementary form of the OR gate. This is the representation of NOR gate, that is OR followed by inverter. This is the truth table we have written, that is for all different combinations of A and B. If A is 0, B is 0, we get a NOR 1. A0, B1, we get NOR 0, A1, B0, we get NOR 0, A1 and B1, we get a output 0. This is a timing diagram of NOR gate. When both the inputs are at low signal, we get a high signal. When both inputs are at high signal, we get a low signal. This is the actual inversion of OR gate. Now we come to the end of this particular video. This is just a recap. What we have seen so far are the basic gates and OR, NOT, NAND and NOR. We have looked into digital representation of each of the NOR gate, of each of the basic gates, Boolean expressions, truth table, inference and timing diagram for all the above set basic gates. Hope you have enjoyed watching this e-content. Thank you.